This is problem number 3 on page 240. Y double prime plus y equals to secant cubed x. Okay, now why does the method of undetermined coefficients not work well here? Actually, I don't think it works at all. It's because when you take the derivative of secant cubed, you're going to create a new function. And when you take its derivative, you're going to create yet another new function. And it's just going to telescope out, and you're going to create more and more complicated functions. In other words, an infinite number of derivatives of secant cubed is going to produce an infinite number of different functions. And we're not going to be able to find all infinite number of undetermined coefficients. There's the problem. So we'll try variation of parameters. And our technique is to first start with the complementary solution. So we look at the characteristic equation, m squared equals plus 1 equals to 0. Which means m squared is equal to minus 1. We solve by taking square root, and we get plus or minus the square root of negative 1, which is plus or minus I, isn't it? Well, we could write the complementary solution this way. It would be c1 e to the ix plus c2 e to the minus ix. Or, as we saw in earlier videos, we can also write this in cosine and sine form. It would be c1 cosine of x plus c2 sine of x. So, now this was plus or minus 2i, we would have cosine 2x and sine 2x instead of what I have up there. Alright, so there's our start. And let me erase all this stuff. Now then, we're going to let y1 be cosine of x and y2 be sine of x. And then our particular solution then, y particular, is going to be u1 times cosine x plus u2 times sine x. Alright, remember it's u1 y1 plus u2 y2. Now in the course of solving by using Kramer's method, we also needed to know what these derivatives are. So y1 prime is minus sine x and y2 prime is cosine of x. There we go. So I think we have about all the ingredients, and the formula that we derived for u1 prime, so let's solve one of these at a time. u1 prime is going to be 0 y2 q of x over a2 y2 prime divided by the determinant y1 y2 y1 prime y2 prime. So if we plug in our ingredients here, we'll have 0 y2 is sine x, and then q of x is secant cubed over a2 is 1, so that's just secant cubed x, and y2 prime is cosine x divided by, we see cosine x, sine x, and minus sine x and cosine x. There we go. So, yeah. Well, as usual, I'm low on board space, and I'm going to have to erase this part, I guess, because we will need this again. And so let's see. This is equal to u1 prime, isn't it? The derivative of the u1 function. Now then, let's work these determinants. So u1 prime will be 0. So this is going to be 0. And then this is minus sine x secant cubed x. All right. And now I think probably we can be productive to think of this as minus tangent x secant squared x. Because if we take out one of the secants, secant is 1 over cosine, of course. So I have 1 over cosine times sine. That sine over cosine is tangent. So I've got minus tangent x secant squared x. And down below, this is going to be cosine squared x. And then minus the negatives cancel. That's plus sine squared x. So the bottom determinant is simply cosine squared plus sine squared, which is 1. So there's u1 prime. It's minus tangent x secant squared x. And to get u1, we'll have to integrate minus tangent x secant squared x dx. And let's see here. The derivative of tangent is secant squared, so we can use that to our advantage. This is the negative sign. Integral tangent x times the differential of tangent x. So the derivative of tangent x is secant squared. So differential tangent x is secant squared x dx. That's this part right here. Here's tangent. There's the negative sign. And so I'm basically integrating something like x dx. I'm just going to get a power of tangent. So u1 will be, and I need to make some room here. u1, when I integrate this, I'm going to get negative tangent squared over 2. All right, minus tangent squared x over 2. So if I take this derivative, just to check myself, I'll get minus 2 over 2. The 2's cancel. So I get minus tangent to the first power times the derivative of tangent is secant squared. So that works out. I use a substitution technique there. Okay, so there's u1. Now let's go find u2. I'll do a little erasing. Well, here's u2. I looked it up. u2 prime rather. u2 prime is this determinant, y1 0, y1 prime q of x over a2. And then the denominator is the same as when we calculated for u1 prime. So we already know that this is equal to 1 in this problem. So I don't have to worry about it. And we'll plug things in here. So y1 is cosine x. And then 0. And then y1 prime is minus sine x. And q of x was secant cubed over 1, so it's just secant cubed x. And again, this was all divided by 1. Actually, it's kind of neat because if you substituted 0 here, you would be okay. Because when we work this determinant, we'll just have this product minus 0 times whatever that is. So we could cheat and put a 0 there. It wouldn't matter. Okay, so I have basically cosine times secant cubed. Well, this cosine will cancel one of the secant cubes, one of the secants rather, and leave secant squared. And then minus 0. So u1 prime, u2 prime rather, is secant squared x. Let me write that up here. So I rewrote u2 prime is equal to secant squared x, which means u2 is going to be the integral of secant squared x dx, and that one's pretty common. That's tangent of x. So now in calculus, when you do this integral, you write tangent x plus a constant c, but we don't have to worry about the constant. It's taken care of other places, I think. In any event, u2 is tangent x. Alright, so let's write out the full solution to this differential equation. It's going to be the complementary solution. So y is equal to c1 cosine x plus c2 sine x, and then minus tangent squared x over 2 plus, oops, sorry, I forgot something, didn't I? Because it's, the particular solution is u1 times cosine x and u2 times sine x. Alright, so let's review that. I took u1 minus tangent squared x over 2 times cosine plus u2 is tangent x times sine. So careful there, that's what y particular is. We have to feed in those other two functions. And perhaps we can simplify this a little bit. So I would be, well, what would that be? That would be c1 cosine of x plus c2 sine x, and then minus cosine times a tangent. We'll cancel the one of the denominators. You know, tangent is sine over cosine. So cosine cancels there with one of the tangents. So we'll get a tangent times a sine x minus tangent x sine x over 2. And then over here we have tangent x sine x. And isn't that interesting? Because these two terms are like terms. We can combine them together. So we're not done. We have one of these minus a half of those. And so how about if I just do this? I'm going to make that a plus and erase that. And this should be our solution. So we will trust but verify. And this is always the fun part. Did I get it right? Alright, y equals to c1 cosine x plus c2 sine x plus 1/2 tangent x sine x. We got it. So, alright. Now you might wonder, could this method be applied if q of x was one of those functions we used in method of undetermined coefficients? And indeed, of course, there's no reason to believe it wouldn't work with those. And in fact, they do have some problems here. Like, for example, number 6 in your book on page 240. The right-hand side is 12e to the x, and which could easily be done with method of variation of parameters. All right, I think I'll take on one more, a bit tougher one here. How about we try, well, I'll let you know in the next video. It'll be a surprise.